Understanding the significance of Niels Bohr's contribution requires stepping back to a time when the structure of the atom was still a mystery. At the start of the 20th century, scientists had only a partial idea of what atoms looked like and how they behaved. They knew that atoms contained negatively charged electrons and a positively charged nucleus, but no one could explain how these parts stayed together without collapsing. The classical physics of that era was not sufficient to describe the atom's internal structure. It was during this period of scientific confusion that Niels Bohr introduced a revolutionary idea that would change the course of physics: the concept of quantized electron orbits. In classical physics, if a negatively charged electron moved around a positively charged nucleus, it should constantly lose energy. As it loses energy, it should spiral inward until it eventually crashes into the nucleus. But real atoms do not collapse. Atoms are stable. This contradiction between theory and observation was a major problem for physicists. Scientists needed a model that explained why electrons could orbit the nucleus without losing energy. Niels Bohr provided the answer by proposing that electrons do not move continuously through all possible distances. Instead, they occupy specific allowed energy levels, which he referred to as quantized orbits. To understand why this idea was so groundbreaking, we need to look at the idea of quantization. In everyday life, motion and energy seem continuous. For example, you can move your hand gradually from one position to another through an infinite number of points in between. But Bohr suggested that inside the atom, things do not operate this way. Electrons cannot exist anywhere around the nucleus. They can only exist in certain fixed orbits that correspond to fixed amounts of energy. These orbits are not physical tracks or rings like planets around the sun, but rather specific energy states that electrons are allowed to occupy. Bohr built his idea on the earlier work of Max Planck and Albert Einstein, who had introduced the idea that light energy is quantized. Planck showed that light is emitted in small packets called quanta, and Einstein demonstrated that light also travels in small energy packets now called photons. Bohr extended this concept to the internal structure of the atom. Instead of energy being continuous, Bohr argued that the electron itself is restricted to discrete levels of energy. This idea solved the stability problem of the atom. As long as the electron stays in one of these allowed orbits, it does not radiate energy and therefore does not collapse into the nucleus. The next element of Bohr's theory concerns what happens when an electron moves from one orbit to another. If an electron jumps from a higher energy orbit to a lower one, it must release energy. Bohr argued that this energy is released in the form of light. Similarly, if an electron absorbs energy, it can jump from a lower orbit to a higher one. This process of jumping between energy levels is what produces the characteristic spectral lines observed in atomic spectra. For many years, physicists had studied the pattern of colors emitted by heated gases, but they could not explain why atoms emitted light at specific wavelengths rather than a continuous spectrum. Bohr's model provided the explanation. Each element has its own set of allowed energy levels, and therefore emits or absorbs light at specific frequencies corresponding to transitions between those energy levels. Bohr's atomic model not only explained how atoms are structured, but also clarified how atoms interact with light. This was a major breakthrough because it connected physical structure and observable behavior. It showed that the microscopic world followed different rules than the macroscopic world. This was the first clear indication that classical physics could not fully describe atomic behavior. Bohr's work marked the beginning of quantum theory as it applies to atomic structure. An important detail in Bohr's theory is that the size of an electron's orbit and its energy are related to something called the principal quantum number, represented by the letter n. The value of n determines the electron's energy level. For example, an electron in the n equals 1 state has the lowest energy, while an electron in the n equals 2 or n equals 3 state has more energy and is farther from the nucleus. This simple numbering system helped scientists categorize and calculate atomic behavior with much greater precision. Bohr also introduced the idea that the angular momentum of an electron in orbit is quantized. Angular momentum refers to the motion of an object that is rotating or moving around a center. Bohr stated that the angular momentum of an electron is limited to whole number multiples of a fundamental constant, known as the reduced Planck constant. This idea was radical at the time because classical theory allowed angular momentum to have any value. By restricting angular momentum to specific values, Bohr was enforcing quantization at a fundamental level. This was one of the earliest signs that the laws governing the atomic world were mathematical, precise, and distinct from everyday experience. The success of Bohr's model became evident when it was applied to the simplest atom, hydrogen. The hydrogen atom contains only one proton and one electron, making it the ideal test case. By applying his quantized orbit theory, Bohr was able to correctly predict the wavelengths of the spectral lines emitted by hydrogen. This agreement between theory and experiment gave strong support to his idea. Scientists now had a model that not only made logical sense, but also produced accurate predictions. This predictive power made Bohr's theory widely accepted, even though it challenged traditional physics. However, it is important to recognize that Bohr's model was not the final answer to atomic structure. Later improvements, especially through the work of Werner Heisenberg and Erwin Schrödinger, modified Bohr's ideas. Heisenberg introduced the principle of uncertainty, suggesting that electrons do not have precise orbits at all, but rather exist in probabilistic clouds defined by mathematical wave functions. Schrödinger developed the wave equation that describes these electron clouds. These later developments refined the understanding of atomic behavior, but they did not erase Bohr's contribution. Instead, they built on it. Bohr's concept of quantized energy levels remains central to modern quantum mechanics. Bohr's original contribution is still seen in chemistry today. Every chemistry student learns about electron shells, energy levels, and transitions between orbitals. These ideas form the foundation for explaining chemical bonding, molecular structure, and the periodic table. Without Bohr's insight into quantized orbits, the entire structure of chemical science would lack its theoretical basis. Bohr's work also influenced technology. Understanding electron energy levels enabled the invention of lasers, which rely on electrons transitioning between energy states to produce coherent light. Quantum theory, built partly on Bohr's model, led to the development of semiconductors, which are essential to computers and modern electronics. Even medical technologies such as MRI scanners depend on quantum properties of atoms. In this way, Bohr's concept of quantized electron orbits did far more than resolve a scientific puzzle. It laid the groundwork for multiple fields of science and technology that define modern life. His idea changed how humanity understands matter, energy, and the structure of reality itself. Bohr's insight marked a turning point in physics, transitioning from classical to quantum thinking. This shift required scientists to accept that the microscopic world obeys its own set of laws, which are often counterintuitive but fundamentally consistent. Bohr's achievement also demonstrates the power of theoretical reasoning. At the time he proposed his model, direct observation of atomic structure was impossible. The tools to visualize atomic behavior did not exist, yet Bohr was able to construct a working model of the atom using mathematical reasoning and logical inference. His model showed that science can advance not only through experiments, but also through deep conceptual thinking. Bohr also emphasized that scientific progress comes from recognizing the limits of existing ideas. He saw that classical physics was insufficient for explaining atomic stability, and instead of trying to fix classical theory, he introduced a new framework. This required intellectual courage and creativity. Bohr was willing to challenge established beliefs because he trusted the evidence of experiments and the logic of quantization. The introduction of quantized electron orbits was not simply a scientific innovation. It was a philosophical shift. It forced scientists to accept that nature at its smallest scale is not continuous and deterministic, but discrete and probabilistic. This new understanding changed how scientists interpret causality, measurement, and the concept of reality. Bohr himself later played a major role in the philosophical interpretation of quantum mechanics, arguing that the nature of atomic behavior depends on how it is measured. His approach became known as the Copenhagen interpretation, which remains influential today. Thus, the first keynote point that Niels Bohr introduced the concept of quantized electron orbits is not merely a statement of fact. It represents the foundation of modern quantum physics. It explains why atoms are stable, how they emit and absorb light, and how matter is organized on its smallest scale. The significance of this idea cannot be overstated. It reshaped scientific thought, empowered technological development, and transformed humanity's understanding of the universe. The acceptance of Bohr's model was not immediate or universal. At the time, the scientific community was divided between those who believed that classical physics could still describe the atom and those who recognized that new theories were necessary. Bohr's proposal that electrons occupy fixed quantized orbits challenged the intuition of many physicists. Yet, the strength of Bohr's theory lay in its ability to match experimental data, especially the spectral lines of hydrogen. This alignment between theory and measurement was powerful evidence that Bohr was on the right track. In science, a theory that predicts real-world behavior accurately carries weight, even if it disrupts established beliefs. This predictive success allowed Bohr's model to gain acceptance and inspired further research into quantum behavior. A key aspect of Bohr's theory was his assertion that electrons could change energy levels only by absorbing or emitting a precise amount of energy. This idea explained the discrete spectral lines observed in experiments. When heated or energized, atoms emit light at specific wavelengths. Before Bohr, scientists could measure these wavelengths, but could not explain why they were not continuous. Bohr's model made the connection clear. Each energy level in the atom corresponds to a specific allowed energy value, and transitions between these levels correspond to specific amounts of light. Energy, the emission and absorption spectra of hydrogen, which had puzzled scientists for decades, suddenly had a logical explanation. This connection between energy levels and spectral lines demonstrated the power of thinking in terms of quantization. Bohr showed that energy is not something that changes smoothly, but something that changes in small, countable steps at the atomic scale. This marked a departure from classical physics and allowed scientists to explore the world of subatomic particles in new ways. In Bohr's framework, the atom was no longer viewed as a miniature solar system, but as a system governed by mathematical rules and discrete values. Bohr's work also had a profound influence on the development of quantum mechanics. While his model had limitations and was later refined, it served as a stepping stone toward a more complete theory. Werner Heisenberg, one of the pioneers of quantum mechanics, was deeply influenced by Bohr's thinking and worked under his mentorship. Heisenberg's matrix mechanics and Erwin Schrödinger's wave mechanics would eventually replace the idea of fixed electron orbits with probabilistic electron clouds. However, the concept of energy quantization remained central. Schrödinger's wave functions describe how electrons are distributed in space, but the allowed energy levels still correspond to the same quantized values introduced by Bohr. In this way, Bohr's core insight survived and became foundational to modern physics. The transition from Bohr's model to the modern quantum mechanical model of the atom is important to understand. In Bohr's model, electrons move in clear circular orbits around the nucleus, similar to planets orbiting the Sun. In modern atomic theory, electrons do not have precise positions or paths. Instead, they exist in regions of probability known as orbitals. These orbitals describe where an electron is likely to be found rather than where it definitely is. This change in understanding did not invalidate Bohr's idea of quantized energy levels. Rather, it refined the model of how electrons behave. The shift illustrates how scientific theories evolve over time. New theories do not always erase older ones, but often expand upon them, correcting limitations while preserving core principles. Bohr's work also influenced how scientists think about measurement and reality. In classical physics, objects have definite properties independent of observation. But in quantum physics, the act of observing a system can change its state. Bohr played a central role in interpreting this aspect of quantum mechanics. He argued that the properties of particles cannot be understood separately from the act of measurement. This perspective, known as the Copenhagen interpretation, emphasizes that physical systems at the quantum level exist in a range of possible states, and measurement collapses these possibilities into a definite outcome. This challenged traditional ideas about objectivity and determinism and sparked philosophical debates that continue to this day. Bohr's introduction of quantized orbits also had practical implications beyond theoretical physics. It provided a framework for understanding chemical behavior. The arrangement of electrons in quantized energy levels explains why atoms form chemical bonds, how molecules are structured, and why elements behave differently from one another. The periodic table, which organizes elements based on their properties, can be understood in terms of electron configurations. Elements with similar configurations have similar chemical behaviors. For example, elements in the same column of the periodic table have similar outer electron arrangements, which determine how they interact with other atoms. Bohr's insights, therefore, helped unify the study of physics and chemistry. Technological progress in the 20th and 21st centuries owes much to the understanding of atomic structure that followed Bohr's work. The development of semiconductors, which form the basis of modern computers, smartphones, and digital technology, depends on precise control of electron behavior in materials. Lasers, used in medicine, communication, and industry, rely on controlled electron transitions between quantized energy states. Nuclear power, medical imaging, and spectroscopy all depend on the principles Bohr introduced. His work did not simply stay within academic science, but became the foundation for innovations that define modern civilization. One of the most important aspects of Bohr's scientific career was his role as a collaborator and teacher. He understood that complex scientific problems required collective effort. At his institute in Copenhagen, Bohr created an environment where scientists could openly discuss ideas, debate interpretations, and challenge conventional thinking. Young physicists from all over the world came to study under Bohr, including Werner Heisenberg, Wolfgang Pauli, and many others who would later shape modern physics. The collaborative model that Bohr encouraged changed the culture of scientific research, emphasizing discussion and shared progress rather than isolated work. Bohr's contributions also extended to global issues. During World War II, Bohr became involved in discussions about nuclear weapons. Although he contributed to early nuclear research, he strongly believed that the knowledge of the atom should be used responsibly. After the war, he advocated for international cooperation and open communication about nuclear science. Bohr recognized that scientific discoveries have ethical consequences, and that scientists have a responsibility to consider how their work affects humanity. His leadership helped shape international discussions about arms control and scientific transparency. The legacy of Bohr's introduction of quantized orbits is not limited to science and technology. It also changed how people think about nature. The idea that reality behaves differently at different scales challenged the assumption that the universe operates according to simple, uniform laws. At the atomic level, behavior is governed by probability, uncertainty, and discrete values rather than by continuous motion and deterministic cause and effect. This realization influenced fields outside of physics, including philosophy, mathematics, and even art. The concept of quantization became a metaphor for understanding that complexity and simplicity coexist in nature. In education, Bohr's model remains a key introduction to quantum ideas. Students learning about the atom begin with Bohr's model because it is intuitive enough to visualize yet accurate enough to explain basic phenomena. Although more advanced models replace the idea of electrons moving in fixed orbits, the concept of energy levels remains essential. Bohr's model provides the conceptual bridge between classical ideas and the more complex realities of quantum mechanics. In summary, the first keynote that Niels Bohr introduced the concept of quantized electron orbits represents one of the most important turning points in modern science. It allowed scientists to understand why atoms are stable, how they interact with light, and how chemical elements behave. It led to the development of quantum mechanics, modern electronics, lasers, and many technologies that shape daily life. It also changed the philosophical understanding of reality itself. Bohr's insight continues to guide scientific thinking and inspires new generations of scientists to explore the fundamental nature of the universe. When Bohr introduced his atomic model, one of the most important achievements was that it provided a clear explanation of how atoms absorb and release energy. Before his work, scientists had been observing the behavior of heated gases and noticing a pattern. When atoms were energized, they emitted light at very specific colors or wavelengths. These patterns were known as spectral lines. Each element had its own unique pattern, almost like a fingerprint. For years, physicists and chemists recorded these spectral patterns, but had no theory to explain why they occurred in discrete lines rather than in a continuous spectrum. Classical physics suggested that atoms should emit energy smoothly across a range, but experiments clearly showed sharp, precise lines. There was a gap between observation and theory, and Bohr's model provided the missing connection. To explain how atoms absorb and release energy, Bohr built on his earlier idea that electrons occupy specific, quantized energy levels. In his model, electrons orbit the nucleus in allowed paths, each associated with a specific amount of energy. The electron cannot exist between these levels. This means that if an electron wants to move to a different orbit, it must undergo a change in energy. This change in energy does not happen gradually, but occurs in a single step. This step is what produces the absorption or emission of energy. When an electron jumps to a higher orbit, it must absorb energy. Conversely, when it falls to a lower orbit, it must release energy. This release of energy occurs in the form of a photon, a small packet of light. This idea directly connected the structure of the atom to observable light. Different energy levels in an atom are separated by precise amounts. So the energy of the photon released or absorbed during a transition must match the difference between those levels. That is why atoms emit or absorb light only at specific wavelengths. The spectral lines are therefore evidence of the quantized structure of the atom. This interpretation brought harmony between theory and experiment. Suddenly, scientists were not just measuring spectral lines, they were understanding them. A key detail is the relationship between the energy of the photon and its wavelength. Bohr used Planck's formula, which states that the energy of a photon is proportional to its frequency. This meant that the exact color of light emitted or absorbed could be calculated. Bohr's model succeeded because it did not only describe atomic structure, it predicted measurable results. When Bohr calculated the wavelengths of the hydrogen spectral lines using his model, the values matched the experimental data already measured in laboratories. This agreement was striking and convincing. It demonstrated that the quantized energy levels inside atoms were not just a speculative idea, but a real feature of nature. Bohr's explanation of energy, absorption, and release also helped scientists understand why atoms stay stable. In classical physics, if electrons were constantly radiating energy while orbiting the nucleus, they would spiral inward and collapse the atom. Bohr's model solved this problem by showing that electrons in stable orbits do not emit radiation. They only emit or absorb energy during transitions. This was a major breakthrough. It indicated that radiation is not a continuous process, but a discrete one, tied directly to changes in electron energy levels. This concept also provided a framework for understanding chemical behavior. The electrons in the outermost energy levels, called valence electrons, determine how atoms interact with each other. Atoms absorb energy to rearrange these outer electrons when forming chemical bonds. Bohr's model gave scientists a way to visualize why certain atoms react and others do not. Atoms absorb energy in chemical reactions to move electrons into new arrangements that allow bonds to form. When bonds break, energy is released as electrons return to lower energy states. This connection between electron behavior and chemistry lies at the heart of modern chemical science. Another important aspect of the absorption and release of energy is that it is not random. Only certain transitions are allowed. Bohr's model provided rules for which transitions can occur. This helped scientists understand why some spectral lines are strong, others weak, and some completely absent. The structure of the atom is not chaotic but organized, and its interactions with energy follow predictable patterns. These patterns reflect the mathematical structure of quantum mechanics, which developed directly from Bohr's work. Bohr's explanation also influenced the understanding of thermal radiation. When substances are heated, their atoms absorb energy. This energy excites electrons, pushing them into higher energy orbits. As the electrons fall back to lower levels, they release photons. This is why heated metals glow, why flames have different colors depending on the substance burned, and why neon signs emit colored light. Every color that appears corresponds to an electronic transition. Bohr's theory turned everyday phenomena into understandable processes rooted in atomic behavior. The model also extended to the understanding of lasers, even though the technology came decades later. A laser works by stimulating electrons to move to higher energy states, and then return in a controlled, synchronized way. The light produced is not random but coherent and focused. This is only possible because electron transitions happen in quantized steps. Without Bohr's explanation of energy absorption and release, the theoretical foundation of lasers would not exist. And yet lasers are now used in surgery, communication, industry, research, and entertainment. Bohr's explanation of atomic energy transitions also contributed to the development of nuclear science. Although Bohr's model applied most successfully to the hydrogen atom, the principles of energy levels carried over into nuclear structure. Inside the nucleus, protons and neutrons also occupy quantized energy states. Nuclear reactions, including those that produce energy in stars and nuclear reactors, can be understood as transitions between nuclear energy levels. When nuclear particles move between states, they emit gamma rays, which are high-energy photons. This parallels the electron transitions Bohr described, showing that quantization is a universal principle. The connection between absorption and release of energy also had philosophical implications. It forced scientists to reconsider the nature of reality. Classical physics described energy as continuous, flowing smoothly like a liquid. Bohr's model revealed that at the atomic scale, energy behaves more like a staircase than a ramp. You cannot stand between steps, you move from one to the next. This discrete behavior challenged assumptions about how nature operates. Bohr's model showed that reality is not always intuitive. It requires abstract concepts and mathematical reasoning to understand. The explanation of how atoms absorb and release energy also helped unify physics and mathematics. To describe energy levels and transitions accurately, physicists had to develop new mathematical tools. These tools eventually became part of quantum mechanics. Bohr did not create quantum mechanics alone, but his work provided essential direction. Quantum mechanics became the language of atomic science, and it remains one of the most accurate and powerful scientific theories ever developed. Bohr's model also marked a shift in how scientific theories were evaluated. In classical physics, theories were judged primarily by how well they explained observed behavior. Bohr's model introduced the idea that theories also needed to predict behavior that had not yet been observed. Prediction became a key measure of scientific success. Bohr's ability to predict spectral wavelengths demonstrated that his model was not only descriptive but also productive. It generated new knowledge. This predictive power inspired confidence in the quantum approach and encouraged further development. Finally, the importance of Bohr's explanation lies not only in the physics of atoms, but in the broader development of scientific understanding. Bohr demonstrated that progress sometimes requires accepting new principles, even when they conflict with intuition. The idea that electrons jump between states in discrete steps challenged classical reasoning, but it revealed deeper truths about the natural world. Bohr's work showed that science advances not only through observation, but also through bold reasoning and conceptual clarity. In summary, the second keynote highlights the central achievement of Bohr's model. It clarified how atoms absorb and release energy. This explanation connected atomic structure to light, chemistry, technology, and the fundamental laws of nature. It provided a direct link between the invisible world of electrons and the visible world of color, radiation, and energy. It remains one of the foundational insights of modern science and continues to shape research, education, and technology today. The importance of Bohr's explanation of energy, absorption, and release becomes clearer when we examine how it changed the direction of scientific thought. Before Bohr, the atom was a puzzle without a clear mechanism for stability or interaction. His model provided a structured and comprehensible system. It showed that the movement of electrons between energy levels is the fundamental cause of an atom's energetic behavior. From this point onward, every explanation of atomic interaction, chemical bonding, radiation, and even technological applications starts from this core principle. One of the major impacts of Bohr's explanation was on the development of spectroscopy. Spectroscopy is the study of how matter interacts with light. By analyzing the spectral lines of substances, scientists can determine their chemical composition. This is especially important in fields where direct sampling is impossible, such as astronomy. With Bohr's energy-level explanation, scientists could now interpret the spectral lines of stars and galaxies to determine their composition, temperature, and movement. The very identification of elements in distant celestial bodies is possible because Bohr showed that each element emits and absorbs energy in its own distinct way based on its electronic structure. This connection between atomic structure and spectral emission allows scientists to study environments beyond the reach of physical exploration. The discovery of helium, for example, occurred not on Earth but in the Sun. Scientists observed an unknown spectral line in sunlight and later identified it as belonging to a new element. Without Bohr's model explaining why elements have unique energy transitions, this kind of identification would remain speculative. Bohr's explanation thus expanded scientific knowledge from the laboratory to the scale of stars. In addition to spectroscopy, Bohr's model shaped the understanding of thermal and electronic behavior in materials. When a substance heats up, the electrons gain energy. This energy is absorbed from the heat source and causes electrons to move into higher energy states. When they fall back, energy is released in the form of heat or light. This explains why different materials glow at different temperatures and why some substances shine brightly when heated while others do not. It also underlies the working of incandescent bulbs, neon lights, LED devices, and many other sources of illumination. The glowing filament of a bulb emits light because it is heated to a point where electrons rapidly absorb and release energy through continuous transitions. The ability of Bohr's model to explain these diverse energy interactions made it foundational in modern physical chemistry. Chemical reactions can be viewed as processes where atoms absorb or release energy to rearrange electron positions. When atoms interact, it is the electrons in the outer energy levels that determine whether bonds form or break. During bonding, electrons must shift from one configuration to another. This rearrangement involves energy transitions. Bohr's model helped establish the understanding that chemical behavior is fundamentally governed by the arrangement of electrons in quantized energy states. Even in solids, where atoms are packed closely together, energy levels play a key role. The outer electron levels of atoms overlap to form bands of energy states. Whether a substance conducts electricity, behaves as an insulator, or acts as a semiconductor depends on the spacing between these energy bands. This concept forms the basis of modern electronics. The behavior of diodes, transistors, microchips, and integrated circuits all relies on the control of electrons moving between energy states in carefully structured materials. Without the understanding of energy levels in Bohr's model, the electronic devices that define modern life, including computers, smartphones, communication systems, and satellites, would not exist. Lasers represent another powerful application of Bohr's principle. A laser works by exciting electrons in atoms to higher energy levels, and then causing them to return to lower levels in a synchronized manner. This produces a beam of light that is coherent, meaning all the photons are aligned and move together in the same direction. The precision and control of electron transitions make lasers uniquely powerful and useful. Lasers are used in telecommunications, medicine, surgery, barcode scanners, measurements, and scientific research. All these applications are rooted in Bohr's explanation that electron energy changes occur in discrete steps that can be precisely controlled. Bohr's explanation of energy, absorption, and release extended even into biology and medicine. For example, the imaging techniques used in hospitals, such as MRI and CT scans, rely on the interactions between energy and atomic particles. MRI uses the energy transitions of hydrogen nuclei in the body's tissues when exposed to magnetic fields and radio waves. CT scans involve tracking energy, emitting substances inside the body. Both depend on an understanding that particles absorb and release energy in measurable amounts. Thus, Bohr's model indirectly supports technology that allows doctors to look inside the human body without surgery. The influence of Bohr's explanation also shaped the philosophical and conceptual understanding of science. Before quantization, scientists assumed that the physical world operated in continuous motion, governed by smooth and predictable forces. Bohr showed that nature has a deeper structure in which actions occur in discrete steps. This required scientists to rethink the nature of change. Instead of seeing energy as something that flows like water, they had to understand it as something that moves in jumps. This conceptual shift opened the way for new thinking in multiple disciplines. Mathematics shifted toward discrete models, chemistry reorganized around electron configurations, and physics moved into a new quantum era. Bohr's explanation changed not only scientific knowledge, but also scientific attitudes. Scientists learned to accept that reality may not align with common intuition. The microscopic world operates differently from the macroscopic world. Precision, probability, and abstract reasoning took precedence over direct observation. This shift encouraged openness to new theories, which later supported the acceptance of more complex quantum mechanical ideas, including wave, particle duality, and the uncertainty principle. Bohr's insistence on connecting theory with observable evidence provided a methodological foundation that continues today. Modern physics often works with systems that cannot be observed directly, such as black holes, neutrinos, or subatomic particles. The principle that theories must align with measurable consequences traces back to Bohr's success in linking atomic transitions to spectral data. His work demonstrated that even phenomena beyond human senses can be understood if they produce measurable effects. This principle remains central to scientific research. The significance of Bohr's explanation becomes even clearer when we consider that it provided the first complete understanding of atomic stability and interaction. The atom was no longer a mysterious object, but a structured system governed by rules. The absorption and release of energy became predictable, calculable, and applicable across all fields of science. Bohr gave the atom a language, energy levels, transitions, spectral lines, and quantization. These concepts remain the foundation of how atoms are described today. In conclusion, the second keynote Bohr's explanation of how atoms absorb and release energy represents a transformation in scientific understanding. It unified theory and experiment, provided the basis for spectroscopy, chemistry, electronics, lasers, nuclear technology, and medical imaging, and reshaped how scientists think about energy and matter. It marked the arrival of quantum thinking and prepared the way for the full development of quantum mechanics. It connected the invisible world of electrons to the visible world of light and color. Bohr's explanation remains one of the critical achievements in the history of science and continues to shape knowledge, technology, and society. When Niels Bohr began his work on the atom, physics was divided into two worlds. On one side was classical physics, which described motion, forces, and energy in terms that seemed logical, continuous, and predictable. Classical physics worked well for everyday objects, planets, machines, sound waves, and light rays. On the other side was a new, incomplete idea known as quantum theory. This emerging field suggested that energy behaved differently at the smallest scales, appearing in discrete packets called quanta rather than as smooth, continuous quantities. Scientists were unsure how to reconcile these two views of nature. Bohr's major contribution was to find a way to connect them, forming a bridge that helped establish the foundation of modern atomic theory. Before Bohr's work, classical physics had run into several contradictions when used to explain atomic behavior. The biggest problem was the stability of the atom. According to classical electromagnetic theory, if an electron orbited the nucleus like a planet around the sun, it should constantly emit energy and lose speed. As it loses energy, the electron should spiral inward until it crashes into the nucleus. This would mean atoms could not exist as stable structures. Yet stable atoms clearly do exist. Everything in the physical world depends on them. This contradiction showed that classical physics alone could not explain atomic structure. Meanwhile, quantum theory was developing through the work of Max Planck and Albert Einstein. Planck introduced the idea that energy is absorbed or emitted in small packets, and Einstein later proposed that light itself is made of particles called photons. These ideas suggested that, at a small scale, energy is not continuous. However, quantum theory was still not fully formed, and it did not yet have a clear application to atomic structure. What Bohr did was take the useful concepts of quantization and apply them to the atom in a meaningful and structured way. Bohr proposed that electrons do not move through space freely and continuously. Instead, they occupy specific allowed energy levels, or quantized orbits. These orbits are stable, meaning an electron can stay in them indefinitely without losing energy. This idea came from quantum theory. At the same time, Bohr used classical physics to describe some aspects of electron motion, such as the way an electron's angular momentum relates to its orbit. Bohr, therefore, did not replace classical physics entirely. He used classical ideas where they were effective, and quantum ideas where they were necessary. This combination allowed him to develop a model that was mathematically workable and physically meaningful. When Bohr introduced his theory, it explained behaviors that classical physics could not. For example, it clarified why atoms emit or absorb light at specific frequencies. When an electron moves from one energy level to another, it must either release or absorb energy in the form of a photon. The energy of the photon corresponds to the difference between the two levels. This principle directly linked quantum theory to observable spectral lines. Classical physics could not explain the discrete nature of these spectral lines, but Bohr's combined model could. Bohr's approach influenced how scientists thought about the limits of classical theories. Classical physics was not discarded. Instead, it became recognized as an approximation that works well for large-scale systems but breaks down at very small scales. Bohr showed that the atomic world follows different rules, and that these rules must incorporate quantization. This marked the beginning of a new era in physics. Classical and quantum theories were not enemies, they were parts of a larger framework. Bohr also introduced the principle of correspondence, which stated that quantum theories must agree with classical physics in situations where classical physics is known to work. This principle helped scientists transition between the two systems. It ensured that quantum mechanics would not contradict classical results at large scales, even while providing new insights at small scales. The principle guided later physicists in developing more complete quantum mechanical theories and helped prevent confusion during this major shift in scientific thought. By combining classical and quantum ideas, Bohr set the stage for the full development of quantum mechanics. His work influenced Werner Heisenberg, who developed matrix mechanics, and Erwin Schrödinger, who developed wave mechanics. Both of these systems provided a more mathematically refined understanding of atomic behavior. Yet both continued to use the idea of quantized energy levels that Bohr introduced. Bohr's model, therefore, became the foundation rather than the final answer, even though later theories showed that electrons do not travel in fixed orbits. The concept of quantization remained central. The combination of classical and quantum physics also shaped the philosophical interpretation of science. Classical physics assumed that objects have definite positions, velocities, and behaviors independent of observation. Quantum theory suggested that at small scales, properties depend on how they are measured. Bohr supported this new view and became a central figure in debates about the meaning of quantum mechanics. His interpretation, known as the Copenhagen interpretation, argued that at the quantum level, nature does not have fixed states until it is observed. This represented a radical shift in how scientists think about reality. Bohr's ability to combine classical and quantum ideas was not only technical, but also conceptual. He understood that science advances when new ideas are integrated with old ones, rather than replacing them outright. He helped the scientific community transition from a classical world, to a quantum world, smoothly, without abandoning the successes of classical physics. This balanced approach helped ensure that physics developed steadily rather than chaotically. The impact of Bohr's synthesis continues today. Quantum mechanics is now the foundation of modern physics, chemistry, and technology. It explains the behavior of electrons in solids, the operation of semiconductors, the behavior of lasers, and the structure of molecules. These practical applications depend on the merging of classical stability and quantum transitions, exactly the relationship Bohr described. His work provided the conceptual bridge that allowed quantum mechanics to develop into a coherent and powerful theory. In summary, Bohr combined classical physics and quantum theory at a critical moment in scientific history. He preserved the useful structure of classical mechanics while introducing the revolutionary concept of quantized energy levels. This combination allowed him to explain atomic stability, energy absorption and emission, and spectral structure. It also laid the foundation for the development of quantum mechanics and influenced the philosophical understanding of physical reality. Bohr's achievement was not simply the invention of a model. It was the creation of a new way of thinking about nature at its most fundamental level. Niels Bohr did not work in isolation. His scientific achievements grew out of conversations, debates, and collaborations with some of the most influential physicists of the 20th century. Among these figures, two stand out strongly: Ernest Rutherford and Albert Einstein. Each of them contributed to shaping Bohr's thought, and in turn, Bohr influenced their ideas. Together, their interactions helped define the structure of modern physics. Bohr first became closely associated with Ernest Rutherford while studying the structure of the atom. Rutherford had recently proposed a new atomic model based on his gold foil experiment. He showed that the atom contains a tiny, dense nucleus with electrons surrounding it. This overturned the earlier plum pudding model that had pictured electrons embedded within a diffuse cloud of positive charge. While Rutherford's model corrected the structure of the atom, it faced a major problem. Classical physics predicted that electrons orbiting the nucleus should lose energy and fall inward, collapsing. The atom, Rutherford had identified the nucleus, but he could not explain how electrons remained in stable orbits. This is where Bohr entered the scientific conversation. He approached Rutherford and joined him in Manchester in 1912. While working alongside him, Bohr began to think about how to solve the problem of atomic stability. He used Rutherford's nuclear atom as the physical framework, and then added the revolutionary idea from quantum theory: electrons have certain allowed orbits and can only change energy in discrete steps. In this way, Bohr preserved the accuracy of Rutherford's nuclear structure while correcting its instability. Their collaboration was a perfect example of how science moves forward through shared ideas, respectful critique, and mutual insight. While Rutherford provided Bohr with the structural model of the atom, Albert Einstein became Bohr's principal intellectual challenger and philosophical counterpart. Einstein had revolutionized physics with his theories of relativity and his explanation of the photoelectric effect, which relied on quantized light energy. However, Einstein remained uncomfortable with the fundamental uncertainty that quantum theory introduced. Bohr, however, defended the idea that nature at the atomic scale does not behave deterministically. For Bohr, the behavior of electrons and photons could only be described in terms of probabilities, not certainties. Their debates became famous. They were not aggressive or hostile, but deeply thoughtful exchanges between two scientists who respected each other and wanted to understand reality. Einstein would pose paradoxes intended to show that quantum mechanics was incomplete. Bohr would respond by explaining that Einstein's assumptions were based on classical expectations, which do not apply at the quantum scale. These discussions played out over many years, especially during conferences in the 1920s and 1930s. Their exchanges forced the scientific community to think more clearly about the meaning of measurement, observation, and physical reality. One well-known story from these debates occurred when Einstein argued that God does not play dice with the universe. He meant that the universe must follow deterministic laws. Bohr replied that Einstein should not tell God how to run the universe. This statement reflects their philosophical differences. Bohr believed the laws of quantum mechanics were not incomplete or temporary. They expressed a fundamental truth about nature. Einstein, meanwhile, believed there must be deeper hidden rules not yet discovered. Their disagreement was not resolved, and it continues to influence scientific debates today. Another area of collaboration for Bohr involved the development of quantum mechanics and the understanding of wave-particle duality. Although Bohr did not create wave mechanics or matrix mechanics himself, he contributed a key interpretive framework known as complementarity. Complementarity stated that particles such as electrons do not have a single, fixed nature. Depending on the experiment, they may behave like particles or like waves, but never both at the same time. This interpretation grew partly out of discussions with Einstein and partly out of earlier discoveries made by scientists such as Louis de Broglie and Werner Heisenberg. Bohr helped unify these ideas and present them to the scientific community in a coherent form. Bohr's collaborations were not limited to theoretical discussions. He also influenced practical scientific developments. During World War II, when many scientists were forced to leave Europe, Bohr escaped from Nazis. He occupied Denmark and found refuge in Britain and later the United States. In America, he worked with scientists involved in the Manhattan Project, including Robert Oppenheimer. Yet Bohr did not see nuclear research only as a technical challenge. He insisted on discussing the moral and political implications of atomic energy. He argued that the scientific community had a responsibility to encourage international cooperation and prevent the destructive use of nuclear power. His efforts reflected the same spirit seen in his earlier collaborations. Science should not be isolated from broader human concerns. Just as he worked with Rutherford and Einstein to refine the meaning of physical theories, he worked with political leaders to shape the role of science in society. His influence in this respect helped shape international discussions on arms control and peaceful applications of atomic energy. The scientific world Bohr inhabited was one of intense change, creativity, and philosophical challenge. Collaborations like the ones Bohr had with Rutherford and Einstein were essential to the progress of physics. No single scientist could have answered all the questions about atomic structure, energy, and quantum behavior. Instead, knowledge developed through conversation, shared research, careful criticism, and the willingness to reconsider assumptions. Bohr excelled at working within such an environment. He was not only a researcher, but also a thinker who valued clarity, precision, and open dialogue. Bohr's approach to collaboration also shaped his role as a mentor. His institute in Copenhagen became a center for young scientists exploring quantum mechanics. Figures like Heisenberg and Schrödinger visited and worked there, continuing the scientific legacy Bohr helped establish. His institute became known internationally as a space of intellectual openness, debate, and innovation. In this sense, his collaborations extended beyond his lifetime, influencing generations of scientists. In summary, Bohr's collaborations with figures such as Rutherford and Einstein were central to his scientific success and to the development of modern physics. Rutherford helped provide the structural understanding of the atom, while Bohr added the quantum rules that made it stable. Einstein challenged Bohr on the interpretation of quantum mechanics, pushing him to clarify and strengthen his ideas. Through these relationships, Bohr helped shape the direction of 20th century science. His work demonstrates how knowledge grows not from solitary effort alone, but from the ongoing conversation between minds seeking to understand the universe. Niels Bohr's scientific career unfolded during one of the most turbulent periods in modern history, and his life was deeply affected by the events of World War II. Although he is widely known for his contributions to quantum theory and atomic structure, his role during the war reveals a different side of him, a scientist confronted with moral responsibility, political danger, and the urgent need to act. Bohr did not simply continue research while the world was at war. He became involved in efforts to protect scientists, preserve scientific freedom, and prevent the misuse of scientific discovery. This part of his life illustrates the struggle of a scientist who understood that knowledge carries consequences. When Germany invaded Denmark in April 1940, Bohr found himself in immediate danger. Bohr was not only a prominent scientist, he was also of partial Jewish heritage through his mother's family. Under Nazi racial laws, this connection put him at risk. His institute in Copenhagen, which had been a center for quantum research and intellectual collaboration, suddenly came under surveillance. Many of Bohr's colleagues and former students were scattered across Europe, attempting to flee or hide. Academic communication was interrupted, and the open exchange of ideas that Bohr valued so deeply became impossible under occupation. Despite the threat, Bohr remained in Denmark for several years, continuing his research and trying to maintain an atmosphere of scientific normalcy at the institute. But even under occupation, he managed to resist in subtle ways. One of the most symbolic acts took place involving the Nobel Prize medals of two German physicists, Max von Laue and James Franck. When the Nazis began confiscating possessions from individuals associated with anti-Nazi positions, there was concern that the gold from these medals could be seized. A colleague brought the medals to Bohr for safekeeping. Instead of hiding them, Bohr arranged for them to be dissolved in acid, leaving no trace. After the war, the gold was recovered and the medals were recast. This act, though symbolic, reflected Bohr's deep commitment to protecting science and scientists from political oppression. Bohr's situation worsened in 1943 when the Nazis intensified their efforts. Denmark's Jewish population was in immediate danger of deportation. Bohr himself received warning that he might soon be arrested. He had no choice but to escape. With help from the Danish resistance, Bohr and his son Aj were smuggled to the coast and transported to Sweden in a small fishing boat. The escape was dangerous. Had they been discovered, they would likely have been imprisoned or killed. Once in Sweden, Bohr was offered safe passage to Britain. However, before departing Sweden, Bohr played a crucial role in securing the rescue of Danish Jews. He met with Swedish officials and urged them to publicly offer asylum. His intervention contributed to Sweden's decision to accept Danish Jewish refugees, allowing thousands to escape arrest. This action demonstrated that Bohr's sense of responsibility extended far beyond academic concerns. He recognized the human stakes of political decisions. Upon arriving in Britain, Bohr entered another sphere of wartime science. By this time, research had begun on the development of nuclear weapons. Scientists understood that the discovery of nuclear fission could be used to produce extremely powerful bombs. The Allies feared that Germany might already be working on such a weapon. Bohr was invited to join the scientific efforts related to nuclear research. He traveled to the United States, where he became involved with the Manhattan Project. His presence was highly valued, not only for his technical expertise, but also for his philosophical insight into the consequences of nuclear power. Yet Bohr did not view nuclear research merely as a wartime necessity. He was deeply concerned about the global implications of the atomic bomb. He realized that once such technology existed, it could not be invented, and the world would forever face the possibility of catastrophic destruction. Bohr believed that the only solution was openness and international cooperation. He argued that knowledge of nuclear science should be shared, not kept secret, so that nations could build trust and prevent arms races. He expressed these concerns directly to political leaders, including Winston Churchill and Franklin D. Roosevelt. His proposal was bold and controversial. Governments favored secrecy and advantage, while Bohr warned that secrecy was itself dangerous. Churchill, in particular, rejected Bohr's ideas and even viewed him with suspicion. Leaders feared that sharing nuclear information could weaken their strategic position. Bohr, however, remained committed to the belief that peace required transparency, not competition. His ideas did not change wartime policy, but they played a role in shaping post-war discussions about nuclear responsibility and arms control. After the war, Bohr returned to Denmark, where he resumed his scientific work and renewed his advocacy for science as a force for peace. He spoke publicly and wrote essays arguing for cooperation in atomic research, and cautioned against political misuse of scientific knowledge. His institute in Copenhagen once again became a center for research and discussion, continuing the intellectual tradition that war had interrupted. The experiences of World War II profoundly shaped Bohr's understanding of the relationship between science and society. He learned that scientific knowledge cannot be separated from ethics or politics. The same theories that explain the structure of the atom can be used to construct weapons of immense destructive power. Bohr believed that scientists must acknowledge this responsibility and participate in decisions about how their discoveries are used. He rejected the idea that science exists above or outside human affairs. Bohr's wartime actions, both quiet and bold, reveal a scientist who recognized that knowledge carries weight. He protected colleagues, resisted oppression, fled persecution, contributed to critical scientific efforts, and spoke out for global safety. His legacy during this period is not simply one of survival or contribution to research. It is one of moral clarity. He understood that science is not only about understanding nature, but also about shaping the world in which humans live. In summary, Bohr's role during World War II was defined by struggle, danger, and responsibility. He protected scientific freedom, worked against oppression, contributed to nuclear research with caution, and advocated for international cooperation. His experiences demonstrate that science is deeply connected to human values, and that the pursuit of knowledge must be guided not only by curiosity, but also by conscience. Niels Bohr, one of the most prominent physicists of the 20th century, did more than just propose a model of the atom. He fundamentally reshaped the way humanity understands the microscopic world. The sixth keynote of his life and work emphasizes his pioneering contributions to quantum mechanics and the philosophical implications of his complementarity principle. This aspect of Bohr's legacy illustrates not only his extraordinary scientific ingenuity, but also his deep reflection on the nature of reality, observation, and knowledge. Bohr entered the field of physics during a period of enormous upheaval and innovation. Classical mechanics, as formulated by Newton, had successfully explained much of the observable universe. Yet, by the early 1900s, experiments revealed phenomena that classical theories could not explain. The behavior of electrons, the emission and absorption spectra of atoms, and other atomic phenomena presented a puzzle that demanded a new theoretical framework. It was within this context that Bohr made his indelible mark. The Bohr model of the atom, introduced in 1913, was revolutionary because it bridged classical and quantum theories. He proposed that electrons revolve around the nucleus in discrete orbits, and that energy is emitted or absorbed only when an electron jumps between these orbits. This quantization concept challenged classical notions of continuity and determinism. However, the Bohr model was only the beginning. As the understanding of atomic and subatomic phenomena deepened, it became clear that a more comprehensive theory was needed, one that could account for the wave-particle duality of matter, the probabilistic nature of quantum events, and the limitations of classical observation. It was Bohr's philosophical insight that guided this transition. Bohr recognized that quantum mechanics required a new conceptual approach. He introduced the complementarity principle, a fundamental idea that asserts the necessity of considering seemingly contradictory properties to fully describe quantum systems. For example, light can behave both as a particle and a wave, but these behaviors cannot be observed simultaneously. The complementary nature of these descriptions is not a failure of theory, but a reflection of the limitations inherent in observation. In other words, the nature of quantum entities is such that our classical intuitions about separability and objective reality must be reconsidered. Bohr's complementarity principle had profound implications for both physics and philosophy. It suggested that the act of observation itself affects the phenomenon being observed, a radical departure from classical physics, where observation was thought to be passive. This idea later found formal expression in the Heisenberg uncertainty principle, which mathematically demonstrated that certain pairs of physical properties like position and momentum cannot be simultaneously measured with arbitrary precision. Bohr's insights helped interpret this principle, showing that uncertainty is not merely a technical limitation, but a fundamental characteristic of the quantum world. Moreover, Bohr's approach highlighted the collaborative and iterative nature of scientific progress. He did not work in isolation. His correspondence and debates with contemporaries such as Albert Einstein, Werner Heisenberg, and Erwin Schrödinger were legendary. The famous Bohr-Einstein debates, in particular, revolved around the philosophical interpretation of quantum mechanics. Einstein's discomfort with probabilistic theory, summarized in his remark, "God does not play dice," contrasted sharply with Bohr's acceptance of intrinsic uncertainty. Through these debates, Bohr defended the Copenhagen interpretation of quantum mechanics, emphasizing the completeness of the theory despite its probabilistic and counterintuitive nature. Bohr's influence extended beyond theory into experimental practice. He consistently advocated for experiments designed to test the predictions of quantum mechanics, recognizing that the interplay between theory and experiment was essential for scientific advancement. Under Bohr's guidance, laboratories became hubs of innovation, where emerging ideas could be rigorously tested. His mentorship of young physicists ensured that his vision of quantum mechanics would influence generations of researchers. Figures such as Werner Heisenberg, Wolfgang Pauli, and George de Hevesy carried forward his ideas, shaping the modern understanding of atomic and nuclear physics. The philosophical reach of Bohr's complementarity principle cannot be overstated. It challenged the assumption that reality is a singular, objectively measurable entity. Instead, Bohr suggested that multiple perspectives, each limited yet complementary, are necessary to form a complete understanding of phenomena. This notion resonates not only in physics, but in epistemology, the study of knowledge. It encourages humility in the face of complex systems, reminding scientists that the tools and methods we use inevitably shape our understanding. Bohr's work in quantum mechanics also had practical implications. His insights laid the foundation for technologies that would transform the 20th century, from semiconductors and lasers to nuclear energy and quantum computing. The theoretical frameworks he helped develop allowed scientists to manipulate atomic and subatomic systems with precision, paving the way for innovations that continue to influence daily life. His vision demonstrates how profound theoretical work can have tangible, transformative effects on society. In summary, the sixth keynote of Bohr's life emphasizes his role as both a scientist and a philosopher. Through the development of quantum mechanics and the articulation of the complementarity principle, Bohr fundamentally altered our conception of reality at the atomic level. He embraced uncertainty not as a weakness, but as an essential feature of the quantum world. By doing so, he challenged conventional wisdom, inspired intense debate, and guided the next generation of physicists in exploring the intricate and beautiful structure of matter. Bohr's legacy in this domain is a testament to his intellectual courage, his philosophical insight, and his unwavering commitment to understanding the secrets of the atom. Niels Bohr's life was not only defined by groundbreaking discoveries in atomic physics, but also by his profound impact on the culture and practice of science itself. The seventh keynote of his life emphasizes his enduring legacy, both in terms of scientific achievement and the humanistic dimension he brought to the pursuit of knowledge. Bohr exemplified a rare combination: the rigor of a meticulous scientist paired with the wisdom of a philosopher, a mentor, and a public intellectual. Examining his legacy allows us to understand not only his contributions to physics, but also the ways in which he shaped the broader scientific community and the moral considerations of research. Bohr's influence on modern science can be traced first to his intellectual mentorship. Throughout his career, he nurtured a generation of physicists who would go on to make foundational contributions to quantum mechanics, nuclear physics, and chemistry. Bohr's Institute in Copenhagen became an international hub where ideas flowed freely, and collaboration was prized over competition. He believed that scientific progress was best achieved in a culture of openness and dialogue. Young scientists, including Werner Heisenberg, Wolfgang Pauli, and George de Hevesy, benefited not only from his guidance on technical problems, but also from his encouragement to think critically and creatively about the philosophical implications of their work. Bohr's mentorship extended beyond scientific advice. He modeled a way of engaging with complexity and uncertainty, showing that intellectual humility is as crucial as technical skill. Another critical aspect of Bohr's legacy lies in his ethical engagement with science. During the development of nuclear physics in the early 20th century, the implications of atomic research grew increasingly political and ethical. Bohr, deeply aware of the potential consequences, advocated for transparency, international cooperation, and moral responsibility in scientific research. During World War II, when the destructive power of nuclear weapons became a reality, Bohr was among the few scientists who publicly discussed the necessity of controlling nuclear technology and promoting dialogue between nations. He believed that scientific knowledge carries responsibilities and that the pursuit of discovery must be balanced with consideration of its impact on humanity. This moral vision distinguishes Bohr from many of his contemporaries and continues to serve as a guiding principle in debates about science, ethics, and policy. Bohr's legacy is also evident in the intellectual culture he helped create. He championed the idea that science is not just a collection of facts, but a way of thinking about the world. The Copenhagen interpretation of quantum mechanics, which he helped develop, illustrates this approach. It requires scientists to consider the limits of observation, the role of probability, and the complementary nature of seemingly contradictory phenomena. By emphasizing that understanding is shaped by perspective, Bohr encouraged a nuanced, reflective mode of inquiry that transcends the laboratory. His philosophical insight that reality at the atomic level cannot be fully captured by any single framework has had implications far beyond physics, influencing philosophy, epistemology, and even debates in cognitive science. Bohr's humanistic approach is perhaps most striking in his commitment to international collaboration. He welcomed students and researchers from around the world, regardless of nationality, fostering a global scientific community. In the interwar period, this was not merely an academic gesture. It was a statement about the importance of dialogue and cooperation in a world increasingly divided by politics. Bohr's Institute became a safe haven for brilliant minds at risk during political upheavals, including Jewish scientists fleeing persecution in Europe. Through these efforts, Bohr demonstrated that science can be both a universal language and a moral force, uniting people in the common pursuit of understanding rather than division. Furthermore, Bohr's life exemplifies the integration of struggle and perseverance into scientific achievement. His work was not linear or effortless. The process of developing the Bohr model, refining quantum theory, and articulating complementarity involved deep challenges, intellectual disagreements, and moments of uncertainty. Bohr faced skepticism from the scientific community and had to defend revolutionary ideas that contradicted established physics. His resilience in confronting these obstacles models the perseverance required in all scientific endeavors. Breakthroughs are rarely immediate, and the path to understanding is often nonlinear and demanding. By confronting and overcoming these challenges, Bohr not only advanced physics, but also set an example of intellectual courage. In addition to his philosophical and ethical contributions, Bohr left a lasting mark on technological and applied science. The theoretical foundations he laid enabled the development of nuclear energy, semiconductor technology, lasers, and even quantum computing. While these innovations were not his direct inventions, the intellectual framework he established made them possible. Bohr's work demonstrates how theoretical insight can eventually lead to practical, world-changing applications, illustrating the often unseen link between pure scientific curiosity and technological progress. Finally, Bohr's legacy includes the cultural and symbolic dimensions of science. He became a public figure representing the values of rational inquiry, dialogue, and ethical responsibility. His writings, speeches, and interviews reflect a scientist deeply engaged with humanity's broader concerns. Bohr's ideas continue to inspire not only physicists, but also philosophers, ethicists, policymakers, and educators. His vision of science as a collaborative, reflective, and morally engaged enterprise remains relevant today, particularly as modern technologies present unprecedented ethical challenges. In conclusion, the seventh keynote of Niels Bohr's life highlights the human dimension of science: mentorship, ethical responsibility, perseverance, and international collaboration. His legacy extends far beyond the laboratory. It encompasses the culture of scientific inquiry, the moral obligations of researchers, and the philosophical understanding of reality itself. Bohr showed that scientific brilliance is most powerful when coupled with ethical reflection, openness to diverse perspectives, and the courage to navigate uncertainty. His life and work remain a testament to the profound ways in which science and humanity are intertwined, offering enduring lessons for both current and future generations of scientists.